Welcome to qnawire.
A horizontal pipe has an abrupt expansion from D1 to D2. The water velocity in the smaller section is 10 meter per second and pressure in the smaller section is 410 kilopascal. Taking the kinetic energy correction factor to be 1.06 at both the inlet and outlet, determine the downstream pressure P2 and estimate the error that would have occurred if the Bernoulli's equation has been used. The kinetic energy correction factor for both the inlet and outlet is 1.06. The flow is assumed to be steady, fully developed and incompressible. The cross-section flow area of the pipe 1 is pi by 4 d1 square. Substituting the value of d1, pi by 4 into 8 into 10 raised to the power minus 2 whole square. The area of cross-section will be 5.026 into 10 raised to the power minus 3 meters square. Then calculating the cross-section area flow for the pipe 2, which is pi by 4 d2 square. Substituting the values, pi by 4 into 16 into 10 raised to the power minus 2 whole square. This is equals to 20.106 into 10 raised to the power minus 3 meters square. Then the velocity of the water using conservation of mass flow, rho v1 AC1 is equals to rho v2 AC2. From here we have to calculate the velocity v2, which is equals to 5.026 into 10 raised to the power minus 3 divided by 20.106 into 10 raised to the power minus 3 multiply v1 is 10, and so the velocity v2 is 2.5 meter per second. The loss coefficient for the sudden expansion is KL equals 1 minus AC1 by AC2 whole square. Substituting the values, 1 minus 5.026 into 10 raised to the power minus 3 by 20.106 into 10 raised to the power minus 3 whole square, and so on solving we get 0.5625. Calculating the head loss HL is equals to KL into V square by 2G. Here G is the gravitational acceleration equals to 9.81. KL is 0.5625 calculated above, multiplied by velocity V1, this is V1, 10 whole square by 2 into 9.81. On solving, the head loss is 2.867 meters. Using the energy equation in the expansion form, P1 by rho g plus alpha 1 into V square by 2g plus Z1 plus the energy transfer in the pump equals P2 by rho g plus alpha 2 V2 square by 2g plus Z2 plus enthalpy or head loss in the turbine plus total head loss. Here Z1 is equals to Z2 and H pump is equals to H turbine. These all gets cancelled out, and so what remains is P2 by rho g is equals to P1 by rho g plus alpha 1 V1 square by 2g minus alpha 2 V2 square by 2g minus HL. We have to solve this expression for P2 and substitute the given values. P2 is equals to 410 into 10 raised to the power 3 plus 1000 into 1.06 into 10 raised to the power 2 by 2 minus 1.06 into 2.5 square by 2 minus 9.81 into 2.867. This will be calculated and the downstream pressure come out to be 431.5 kilopascal. Now writing the Bernoulli's equation, as P1 by rho G plus V1 square by 2G plus Z1 equals P2 Bernoulli by rho G plus V2 square by 2G plus Z2. We have to find the pressure P2 Bernoulli from here. P2 Bernoulli is equals to P1 plus rho into V1 square by 2 minus V2 square by 2. Substitute the values. P1 is 410 into 10 raised to the power 3 plus 1000 into 10 square by 2 minus 2.5 square by 2. We will solve this expression. The error in the Bernoulli, we have to find first the pressure. P2 Bernoulli is 456.875 kilopascal. Now the error in Bernoulli's equation is P2 Bernoulli minus P2. Substitute the value. 456.875 minus 431.5 kilopascal. This is 25.375 kilopascal is the error in Bernoulli equation. Finding the error percentage, which is equals to P2 Bernoulli minus P2, 456.875 minus 431.5 divided by 431.5, and the percentage error in the Bernoulli equation is 5.88%.